This one is C10H11O2Br. This would have 5 double bond equivalents. We have a 4H in the aromatic region, that's going to be C6H4, two things connected to the aromatic ring. We'll have two CH2 groups and a CH3 group. What's left over? We've got a C, two O's, a double bond, and a Br. That would indicate we have a C double bond O. We have an O and a Br left, so we have an O here and a bromine, and that should be all of the pieces. Now we can figure out where things go. What we know is that we have a CH2 connected to CH3. There's only one CH3 group here. We know there's going to be a CH2 group connected to it. The reason we know this is because the CH3 has 3 peaks, suggesting that there must be 2 adjacent hydrogens. So that's why I'm putting the CH2 here. I know that the CH2 can't go here, because what would happen then is that this CH2 would see both the CH3 and the CH2 and would come up as being 6 peaks because it has 5 adjacent hydrogens. So something's going to have to be separating that CH2 from the rest of what we're seeing here. Looking at the rest of what we're looking at, we have a CH2, the CH2 group that's next to the CH3, this one here, the one that's got 4 peaks, is at 4 ppm. Now what we know is that groups that are around 4 ppm, for example this CH2 directly connected to this oxygen, will appear at about 4 ppm. And then a CH3 directly connected to a C double bond O, for example, will appear between 2 and 2.5 ppm. In our specific example, this 2H, the one that's got 4 peaks, the one that is next to this CH3, must also be next to the oxygen. Now I know that's fairly subtle, but that's something that we can observe directly from this spectrum. Again, this CH2 has 4 peaks, so it's next to the CH3. But because it's at 4 ppm, we also know it's directly connected to an O. So now we can go ahead and put the rest of our compound in here. Now you might be wondering why the ordering of this would have to have the C double bond O here and then the CH2 and the aromatic ring here and the CH2 here. Well, the story is kind of told by what's going on here in the aromatic region. Now while I know these examples I'm showing you here have to do with a singly substituted aromatic ring, the same thing applies to disubstituted aromatic rings. When you've got a C double bond O attached to the aromatic ring, you'll notice that it splits it into 2 peaks, and that those peaks are centered at around 7.5 ppm. When there is an alkyl group attached to the aromatic ring, you'll notice that it's just a single peak, and it's going to be somewhere between 7 and 7.5 ppm. Now because this peak is over here near about 7.8 ppm, I would say that the C double bond O has to be connected to the aromatic ring, and I would be inclined to leave it like that. The other clue we have here as well is where the CH2 is. According to the correlation chart, anything connected to a bromine is going to appear somewhere between 3 and 4 ppm. And you'll notice we have the CH2 peak at about 3.5 ppm, suggesting that's next to the bromine. So that would tell me that this is probably going to be our structure.